From KUNC and the NPR network, this is In The NoCo. I'm Erin O'Toole. For people in much of the world, snakebite is a life-threatening condition. We don't think about it much in Colorado, where a nasty rattlesnake bite might send the occasional hiker to the emergency room. But the World Health Organization estimates that as many as 138,000 people from other parts of the globe die from venomous snake bites each year. And while antivenom can be used to treat snake bite, it's often costly and difficult to produce. An expert at the University of Northern Colorado in Greeley hopes to change that. Stephen Mackesy is a professor of biology, and he's part of an international team that recently announced a breakthrough in the production of antivenom. The science behind it is complex, as you'll hear in a minute. But the new technology could save lives by making antivenom cheaper to manufacture and available in larger quantities. Mackesy and his team recently published their findings in the journal Nature, and we wanted to hear about this important research happening at his lab in Greeley. Working in a lab with venomous snakes sounds potentially quite dangerous. How do you limit the risk?
Well, for the most part, I'm the only person that has hands-on handling of the snake, and the only hands-on that we have with them is when we do the extraction process to take venom from the glands and then have raw material to work with in the lab.
Some snakes, like cobras and mambas in parts of Africa, can be lethal. Mm-hmm. They can also cripple someone who gets bitten. Talk a bit about how that affects life in regions with particularly dangerous snakes.
Well, many of these snake bites occur in very rural settings where there is very limited access to any kind of clinic. And further, there's very little access even to antivenoms that are effective. So what happens is these people, if they don't die outright, they often have life-changing alterations to their body parts, typically a foot or leg or a hand or an arm. And that, these people are living in rural agrarian societies. They really are dependent on physical ability to work their crops, to do whatever they might be doing, work with the cattle or other animals that they're using. And so if you suddenly have a situation where the person has lost use of a limb or a foot or something like that, it's critically problematic for that person.
Well, help us understand the state of antivenom production as it currently stands. Scientists do know how to produce antivenom, but it's a cumbersome process that often involves treating horses or alpacas until they're immune to venom and then extracting the animal's blood to make the antidote for people. Talk about why that is a difficult or inefficient process.
With the antivenoms, we produce them historically, just like you said, in a large animal like a horse, a sheep, an alpaca, something like that. And that's a methodology that basically was first invented about 120 years ago.
Wow.
Now, on the one hand, if something works, that's great. Why change it? But on the other hand, we know that the efficacy and the effectiveness of those antivenoms could be increased tremendously and need to be increased tremendously because there's a lot of variation in the venom biochemistry of the snakes, such that just because we used a cobra from this part of Africa or Asia to produce our antivenom, in another part of the country, the same country sometimes, we can have a variant that is very, very different. And so the antivenom is not as effective.
Well, this brings us to your work. You and a team of scientists from around the world developed a process to synthesize antivenom using proteins. You told our producer that once you figure out the recipe, the production process is almost like brewing beer. Without getting too technical, what makes this such a breakthrough?
Well, perhaps as simple as brewing beer is a little bit of an oversimplification, but it does have some similarities at the end point. And I have to stress that many, many people, over 35 individuals, were involved in this work to take it to the place it is right now. And so we're starting with that same basic premise, that is, using a large animal, in this case, an alpaca or a llama, to produce antibodies. But these are special antibodies in the sense that they're much, much smaller than our typical antibodies that we would produce if we were exposed to venom or exposed to a bacterium or something like that.
Okay.
And so these have some distinct advantages, and we can produce them and harvest the blood because these animals are large enough. We can take, say, a liter of blood without harming the animal at all, and then purify the antibodies from that. So there's a number of steps along the way, and I'll spare you the details on that because it gets rather involved and complicated. But once we have those antibody genes inserted into something like a bacterium or into a yeast, then that's where the analogy to brewing beer is. We're using yeast to ferment our materials for brewing beer, and the same kind of cells, not the same type exactly, but similar, produce these proteins for us, and then they'll secrete them and we can purify them from our brew batch. At that point, then, we have a source that is free of any other animal, any other alpaca that was necessary to get the initial nanobodies, as it were.
And it sounds like in the end, it allows you to produce much larger quantities of antivenom than you would using the animals.
Yeah, this is the kind of technology that can be scaled up very readily to produce huge amounts of this material.
And it sounds like at a lower cost, too. Is that fair to say?
Considerably. Now, all that research and development time and effort, of course, is very intensive. But once you have that final product, if we had something that cost $3 to $5, for example, per dose, that would be a definite advantage because right now, antivenoms, one, are limited, and two, tend to be very, very expensive and way out of the range of what is financially possible for most people in rural countries around the globe that are the ones that most at risk to envenomation.
Oh, that's incredible. Steve, one of your contributions to this project was testing the antivenom with mice. Mm-hmm. What was that moment like when you saw the results?
Well, the thing that was most impressive is that this recombinant antivenom actually can rescue mice from the lethal effects of the entire venom of not just one species of snake, but 17 different species.
Wow.
These are lethal doses to the mice and to humans for that matter. But with this nanobody-based antivenom, they're essentially 100% rescued.
I have to ask, did this instill, a super confidence in the mice? Did they strut around in front of the snakes? Like
we would look in the cage and they were flexing their muscles and showing off for each other. Oh yeah, on a regular basis, just like mice always do. So.
Exactly. Stephen Mackesy of UNC helped develop a better method for creating antivenom to treat snakebite. Steve says the antivenom he worked on is not effective against rattlesnakes like the ones we see in Colorado. So that may be a project for the future. We'll put a link to more about Steve's research in our show notes and at KUNC.org. That's it today for In The NoCo. Have a great Thanksgiving holiday. We'll be back next week. I'm Erin O'Toole. Thanks so much for listening.